All right, I think we can start. So first of all, welcome everybody to this week Autonomy Talk. Today is a pleasure to have with us Nicolas Lanzetti, who is a PhD candidate at the Automatic Control Laboratory at ETH Zurich, under the supervision of Professor Florian rfler. So briefly about him, he received his bachelor and master degrees in mechanical engineering with a focus in robotic systems and controls from ETH Zurich. He was a visiting researcher at MIT and Stanford University, and his current research interests include optimal transport, gradient flow in Wasserstein space, with application in control theory, robust optimization, and game theory. He is the recipient of the Willis Tudor Prize, the ETH Medal, and the SVR ASRO Award for his master thesis, and the Best Paper Award at 2021 ITSC conference. So with no further ado, I think the stage is yours, Nicolas.
Hi everyone, hi Alessandro, and thank you so much for the kind introduction and for having me today. My name is Nicolas, and as Alessandro said, I'm a PhD student with Florian rfler at ETH Zurich at the Automatic Control Laboratory. And this work is actually sponsored by NCCR Automation. So today I'd like to talk a bit about dynamic programming when your system is as a state which is a probability distribution. And our main tool of interest for today will be optimal transport. And most importantly, our application of interest will be the one of multi-agent systems. This is joint work with Antonio Terpin, a student of mine, and Florian rfler, my advisor. So the setting for today will be the following. We have some sort of environment. Here you see a grid with some holes, some obstacles here and there. And what we would like to do is to steer a fleet of robots, here a fleet of drones, from an initial configuration, the red one, to a target configuration, the blue one. Of course, here for illustration purposes, I'm using a grid. I'm just using a finite number of robots, but in principle, our setting works in the Euclidean space, in any space like Rn, or in larger grid, smaller grid, whatever you want. And I guess the obvious question is, this seems like a very well studied problem in control or robotics. So why do we need to talk about probability distributions to talk about this problem? So why is this a good language for us? And the answer is actually fairly simple. It turns out that you can take any fleet of robots or any stochastic system and capture the state of such a system by a probability measure. So let me illustrate this principle via a few examples. So if you have a finite fleet where you have one robot at the position -2, one robot at the position -1, and one robot at the position 1, well, then you might want to say that the state of your system is this probability distribution. You have 1/3 probability of being at -1, 1/3 probability of being, of -2, 1/3 probability of being at -1, 0 probability of being at 0, and 1/3 probability of being. And you can think of this probability distribution as if you sample one robot, just take a random robot, and of course you have 1/3 probability of getting the robot at -1, and so on. Or alternatively, you could say, well, 1/3 of my fleet will be at -2, and so on. If you have a bunch of robots, you might want to take the limit to infinity, and then you might want to say that you have a continuous distribution that models your system. And of course, this is this so-called mean field approach, and this works well when your field is infinitely large. For instance, a very large population. So I'm not gonna advocate for one approach or the other. Both approaches fall in the framework that I'm gonna present today. They're both valid for us. And finally, you have the one of stochastic systems, where the evolution of your system is uncertain, and also in this case, you want to use some sort of probability measure to capture the state of your system. Good. So hopefully this convinces you that using or studying such problems using probability distribution is a feasible way or a feasible angle of attack to study them. And hopefully in the rest of the talk, I will convince you that it's actually fairly convenient to pay the extra price that the mathematics poses us to work in the probability space, because there's a bunch of nice properties that this allows us to derive. So let's go with the probability space. And before we actually dive in the control problem, I need to give you some very short preliminaries in optimal transport, which is actually going to be the main tool that we will be using for the analysis of such problems. So classically, optimal transport is defined as the problem of sending some croissants, some bread, from bakeries in Paris to coffee shops in Paris. The bakeries would produce the bread and the coffee shop would actually sell it to the customers. Here I'm going to go the Swiss way and present you optimal transport with cheese and fondue. So imagine you are in this place in Switzerland. This is in the north of Ticino, right before the Gotthard. And you have two locations where cheese is produced. One is called Alpe Piotta, and it's located at the position X1, and it produces 0.3 of cheese. The other place is Cadonigo. It's located at the position X2, and it produces 0.7 of cheese. Of course, I'm assuming the total rate production of cheese normalizes to 1. This is without loss of generality. You could think of 30% of the cheese is produced here, and 70% of the cheese is produced here. Good. And then you have a bunch of places where people would come and eat some fondue, for which the cheese is required. Here you see 3 places. These 2 are mountain huts. And in the first one, 20% of the cheese is consumed. In the second one, 30%. And then you have a very nice village where actually you only reach by foot. You cannot drive there, called Chess, where half of the cheese is consumed. And the question you are confronted with is the one of where should the cheese go? So given that I produce the cheese here, which cheese should go where? And of course, that you have many options. You could say, well, I think that the cheese produced at Alpe Piotta, here we produce 0.3. So this 0.3 should directly go to Campotencia because there the demand is 0.3. So we just send cheese here, and then we split the cheese produced at Cadonigo equally between the 2 other locations. This is, of course, a possibility. Or someone else could say, well, this Alpe Piotta is very close to Chess, so it really makes sense to deliver that cheese there because there's not so much road to do, and then we'll take care of the rest. And in general, there's infinitely many ways you could deliver the cheese, and probably you want to look for the best one. So you look for a gamma that tells you how much cheese goes from which location to which location. This gamma has to satisfy some constraints. For instance, the amount of cheese that is delivered from Piotta should be exactly 0.3 because there you produce 0.3, so it cannot be more in particular. And the amount of cheese that arrives at Campotencia, for instance, should be 0.3 as well, because the demand rate there is 0.3. So if you deliver less than that, there's not going to be enough cheese. So these are, of course, constraints that you need to satisfy when you find the optimal matching. And then what you want probably to do is to minimize the transportation effort. And we capture the transportation effort via this function G. So this function G tells us how much we pay when we deliver cheese from the location xi to the location yj. So a standard choice, of course, is the Euclidean norm. You could say the distance, the effort is actually the distance between the 2 locations. So delivering from Piotta to Campotencia, you would pay x1 minus y1. This is, of course, a possible choice. Probably in an alpine environment, you would want something more sophisticated because you also care about the altitude difference. You also care about the quality of the trails and other factors that cannot be captured by the Euclidean distance. So in general, you want to allow a very general function G that you can actually tune. So your objective value is to, the total amount that you pay is the distance, or let's say the transportation effort times the quantity that you transport. Good. So for conveniency, we write these two constraints as capital gamma. We write we say that the distribution of cheese production is called mu. So it would be 0.7 here and 0.3 here. The distribution of fondue consumption is nu. And we call this object K, G, mu, nu. So K is a letter that we use to emphasize that this is the so-called Kantorovich problem. Kantorovich was the first one that formulated this problem. So this motivates the K. The G is the function that we use to quantify the transportation effort. So it's the function that we have in the objective function. Mu is the distribution of cheese, and nu is the distribution of the fondue places. And more compactly, we, in general, cheese can be produced at more than 2 locations. It could be produced at infinitely many locations. So the math imposes us to replace all sums with an integral. But that's just our shorthand notation to write the problem that I just described. And again, let me emphasize that this function G is called transportation cost, and it's actually the cost that you pay to go from one location to the other. Good. So why should we care? So why is this problem any interesting for us? So in the end, we're doing multi-agents control. So why is optimal transport an important problem for us? And I'm gonna tell part of the story today. The other part, or part of the story now. The other part will come later. And essentially, this optimal transport problem allows us to say how close two probability distributions are. So if they are very close, hopefully this number will be small. If they are very large, this transportation number, if they're very far, this transportation number will be much larger. And since, every fleet configuration can be modeled as a probability distributions, optimal transport directly gives us a way to quantify how close two fleet configurations are. So again, let me do this through an example. So you have a target location with 2 flags. And then you have a fleet consisting of 2 octopus. So you could imagine that here the fondue the cheese is produced, and here the fondue is consumed. And the optimal thing to do would be to send this octopus here and send this other octopus there. And you see that if to quantify the transportation error you use the standard squared Euclidean distance, well, then you get that the distance between the fleet of octopus and the 2 flags is equal to 44. Just a number, not very insightful. But then if you take a second fleet, a fleet of koalas, which intuitively at least is actually much closer to the goal, and you repeat the argument, so this koala would go here and this other koala would go there, just because the other way around would be more costly, you see that the transportation cost decreases to 10.5. So intuitively, we got closer to the end configuration, to the target configuration, and optimal transport is telling us exactly that. So you started with a cost, a distance of 44, and now you're down to a distance of 10. If you go to extreme with this fleet of kangaroos, then you would of course match this kangaroo to this flag, this second kangaroo to the other flag, and indeed you get a distance of 0. So there's essentially you have nothing to transport. Everything is already at the right location. So again, the kangaroos are exactly where they should be, and we see that this optimal transport cost gives us a distance of 0. So this simple empirical observations can actually be made rigorous. So if you take your transportation cost to be a distance, well, then your optimal transport problem will actually be a distance on the probability space. So this is not only intuitive in the sense that whenever we play around with some simple fleets, we get the behavior we want, but this can be made rigorous in the sense that the object we are dealing with, namely this optimal transport problem, really gives us a notion of distance between probability distributions, and therefore between fleet configurations. So hopefully this convinces you that this is a convenient tool to do control, because we have for free essentially a way of comparing fleet configurations. So before jumping to the actual control problem, there's a last setting that I would like to present to you. And so going back to the map, so we have the cheese production locations, we have the fondue consumption locations, but of course you can imagine that for a nice fondue you might also need some wine, and wine might be produced at 2 other locations. So before we had to match the cheese with the fondue, but now we have to match the cheese, the fondue, and the wine. So before we were matching 2 probability distributions, but now we are matching 3. And this problem is a so-called multi-marginal transport problem. So now we have 3 probability distributions that are involved: mu, the cheese; nu, the fondue; and eta, the wine. And again, you have a transportation cost, which now is a function, of course, of the location of the cheese, the location of the fondue, and the location of the wine. And of course, you can go further. You can say, well, I also need some bread, so I need a 4th marginal. I need a 4th probability distribution. And now you get an optimal transport problem with 4 marginals. And of course, this holds for any n. So in general, you can have n marginals, so n items that you would like to match. Good. So this brings me to the conclusion of this short optimal transport summary. So let me iterate on the 3 items that we got to know. So we started with the optimal transport problem. So with cheese, with fondue, and we wanted to somehow match them in the most convenient way. And this was, took the form of this problem. Thereafter, we saw that this optimal transport problem is not only a pictorial problem between cheese and fondue, but is actually useful to quantify the quality of fleet configurations. And we saw this with the example of these 3 fleets: the fleet of octopus, the fleet of koalas, and the fleet of kangaroos. And we saw that the closer we're getting to the target, the lower this optimal transport cost would be. And finally, we said, well, in general, you might not want to match only cheese and fondue, but maybe also wine and bread. And therefore, we got this multi-marginal formulation of the optimal transport problems, where instead of only 2 items, you have in general n items that you would like to match. Good. I think it's a good time for me to pause for a few seconds and ask you guys if there are any questions or any doubts on what I presented so far.
Yeah. Nicolas, just a clarification, but isn't this the same as the Wasserstein distance?
Yes. So
in the case P is equal to 1? Yes,
correct. So when you pick this G, this transportation cost G to be a distance, so a true distance, then you would get the so-called Wasserstein distance, so the so-called type 1 Wasserstein distance. If you pick a G to be a distance to the power of 2, for instance, the squared Euclidean norm, then you need to take a square root, let's say here, to get a distance, to get the so-called type 2 Wasserstein distance. And you can tune the exponent the way you want. And yeah, this is the Wasserstein distance. Yeah, thanks for the question.
Nicolas, a follow up on that. Does G need to be like a proper distance, or it can be also something like a quasi-metric? Does it need to respect symmetry, for example?
So in general, it depends what you want. If you want a distance on the probability space, then your G should actually be a distance. If you just want a transport problem, then you can put any G you want. So there's 0 assumptions a priori. You will actually see later on that we will put a quite an object which in general is non-symmetric, doesn't satisfy any triangle inequality there, but this will be helpful.
Thank you.
Good. So let's go back to our control problem that, we started with fleet of robots or drones in a grid, and somehow we need to write now this problem in the probability space. So let me make this problem a bit easier. So I only have a state space with 3 cells: the cell -1, the cell 0, and the cell +1. And I have m robots, in this case 8 robots, that are somewhere over these 3 cells. So here I have 3 robots at -1, 2 robots at 0, and 3 robots at +1. So yeah, very simple settings. So for each robot, I have 2 options. I can either say, well, my robot will have to go to 0, or I can say my robot can switch and go all the way to the other side. If a robot ends up at 0, it will stay there forever. So this is also, mathematically we can capture this with via these dynamics. You see that if xk is 0, then f of xk will be 0 forever. So you cannot escape the cell at 0. Whereas if you pick the input -1, then you would go from x to -x. So from +1 to -1, or to -1 to +1. Of course, I'm not claiming this realistic setting. Of course, in reality, you wouldn't have something like that, most likely. This is just a way for me to illustrate the whole machine. And then let's say that the goal is to steer half of the robots to -1 and half of the robots to +1. Of course, this target might be too ambitious, because once you are at 0, you cannot escape from 0. So in particular, these 2 robots at 0 will be there forever. So maybe we'll not make it to this goal, but at least we want to get as close as possible. And on top of that, if possible, we also would like to minimize the input effort. So this is the goal that I'm prescribing to this problem. So what's the modeling with probabilities? So the first ingredient that we need to take care of is the state of the system. And we saw before that the state of a multi-agent system can be modeled via probability distribution. So if you have something like that, then you would have 3/8 probability of being in the first cell, 2/8 of being at 0, and 3/8 of being at +1. In other words, 3/8 let's say percent of the robots are at -1, and so on. Or maybe you have something like that, and in this case you would say that 1/2 probability of being at -1, 1/2 probability of being at 0. Or equivalently, 50% of the robots are at -1, and 50% of the robots are at 0, and no robot is at the location +1. Good. So let's go to the input. Here, the question, things are slightly more complicated. So the input for us takes the form of what we call the state input distribution, which we call lambda, and which is the probability of being at a state x and applying the input u. So again, let me illustrate this via an example. So this is a possible gamma, also a possible lambda, probably not, possibly not a very good one, but a possible one. So this lambda would tell us that 0.2%, 20% of the robots are at -1 and will apply the input 0. 30% are at -1 and would apply the input -1, and 50% are at 0 and will apply the input 0. So here you see that at 0, all the robots apply the same input, at least according to this state input distribution, whereas at -1, there's some splitting happening. Some robots will apply the input 0, and some other robots will apply the input -1. Also, if you sum over the inputs, you also get the state distribution. So from this lambda, we can automatically read that 50% of the robot are at -1, just by summing over the first row, and 50% of the robot are at 0, and no robot is at +1. Another possibility would be this second lambda, where all the robots at -1 would apply the input -1, and all the robots at 0 will apply the input 0, and no robot again is at +1. So these are just two, feasible inputs for us and for our field. And then the system dynamics, so the probability distribution, evolves according to this push-forward operator, which is for us just a fancy way of doing something very natural. So if you apply this first input lambda1, well, you will end up with, the robots at 0 will stay at 0 just because you cannot escape the cell at 0, whereas the robot at -1, which apply the input 0, will also go to 0. So in the end, we will have 70% of the robot at 0. The 30% of the robot, this 3/10, was at the state -1, apply the input -1, so it will go to +1, and this justifies this 3/10. So in this case, we'll end up with 70% of the robots at 0 and 30% of the robots at +1. With the second input instead, the robots at 0 will just stay there, just because once you are at 0, you will stay at 0. And the robots at -1, which is 50% of the fleet, will go from -1, we'll apply the input -1, so it will go to +1, according to our dynamics. So you will end up with a state distribution, which is 50% of the robot will be at 0, and the other 50% of the robot will be at +1. So this is compactly written with this notation of push forward of the probability measure, but the machinery going on in the background is exactly this one. Good. So then we have some cost. So when we do control, we have an horizon, a finite horizon, and we have a terminal cost, so a cost at the end of the horizon. And since for us, so we've just discovered that optimal transport is a very good way of quantifying the quality of a fleet configuration, then it does make sense to take optimal transport as a cost. And in particular, I take an optimal transport cost between the state at the end of the horizon and a reference that in our case will be 50% of the robot at -1 and 50% of the robot at +1. So in this case, of course, my tuning object is this transportation cost. So I can decide how much it costs to deliver the cheese from one location to a fondue location. And in this case, I'm just going to take the standard Euclidean norm. So delivering cheese from the location xn to the destination Rn will just cost xn minus Rn in absolute value. And as arose from the question before, if you take this G, if you take this transportation cost, your optimal transport cost will actually be the Wasserstein distance. Good. Then we have a stage cost. So this is a cost that we pay throughout the horizon at every time step. And in this case, I'm prescribing that the cost, throughout the horizon, I don't care about the distance from a reference. So there's no reference there. I only care about the input effort. So the input that I consume to make my robots behave the way I want them to behave. And so in this case, G will only penalize the input. And you can prove that if since the reference does not appear in here, then the optimal transport problem, it doesn't become an optimal transport problem anymore, but collapses to unexpected value. So by doing that, I'm actually penalizing the average input effort. And of course, then you can multiply this average by the total number of robots, and this would give you the total input effort of the fleet. Good. So in a more compact notation, this is our problem setting. So we want to find the optimal state input distribution. So this is telling me the probability of being at a state and applying an input. Of course, this state input distribution should be compatible with the state distribution. In particular, if I take the first marginal, if I sum over all possible inputs, then I should get the probability of being at a state, which is something we write compactly in this form. Then we have some system dynamics, which are given by this push-forward operator that we got to know before. Then we have a terminal cost, which is an optimal transport discrepancy from a given reference. And then we have a stage cost, which is also an optimal transport discrepancy from a reference. So this is the problem that we brought down. And when we did that, we were actually quite optimistic because this really looks like a standard optimal control problem, but in the probability space. So your state is a bit more complicated. It's possibly an infinite dimensional space. So you need to be a bit more careful. But it turns out that the standard way of attacking this problem, namely dynamic programming, does hold even in probability spaces. So what we initially thought was, the way to go is to, just use dynamic programming, just using the classical dynamic programming algorithm and get a solution. So you would initialize your cost to go with the terminal cost, and then run the standard dynamic programming iteration to get the cost to go at time k. This is about finding the optimal state input distribution. You have your stage cost, and then you have the cost to go at the, let's say, at the next time step. So this does work. This does give you the optimal solution if you're able to solve that. But if you look at this dynamic programming iteration, you see that every time you suppose we don't want to optimize over lambda. So we don't care about finding the optimal lambda, but we care about computing this number here. So we soon realized that only to compute this first bit, what you need to do is to solve an optimal transport problem. So you need to solve a fondue and cheese problem, or cheese and fondue problem. And this is only to evaluate the quality of a given lambda. If you want to optimize over that, you probably need to solve a bunch of these transportations problems, which in practice will be prohibitive. So we soon realized that this problem was indeed giving us the optimal solution, but was in practice impossible. Also, the shape of the cost to go was a priori any function in the probability space. So a very complex object that was somehow was making the problem even more difficult. So how do we do? Well, it was a bit frustrating, to be honest, because initially we even tried very simple settings like the 1D setting, quadratic cost, linear dynamics, and even in these simple cases we couldn't get a closed form solution. So what we decided to do is to completely change the approach. And for this new approach, we needed an auxiliary problem. So here I'm replicating the problem that we have. So an optimal control problem with optimal transport as a terminal cost, optimal transport as a stage cost, the dynamics that we've just described. And from this problem, we decided to write down, sort of the same optimal control problem, but now in what we call the ground space. So for us, the ground space is the space on which the probability distributions live. So in this case, the ground space will be xk. And we took this g, we put it here as a terminal cost. We took this gk, we put it here as a stage cost, and we took the dynamics and put them as a dynamics. So this problem is a problem where there's no probability distributions involved. So this is a standard problem that in the case of of a grid, you would just need to have your dynamic programming table. You would just fill this table, and this would give you the optimal solution. So again, we can use dynamic programming here. DPA is very well studied. Its approximations is also very well studied. So if your state space becomes very large, then you can try to approximate it with proximate dynamic programming. You can try to use neural networks to find an approximate solution. These are all very well studied problems in the literature. In some cases, for instance, if you put everything to be quadratic and your dynamics to be linear, then you're even able to construct a closed form solution for the problem, standard, let's say, linear quadratic regulator. So essentially, the ingredients that we have are, in the ground space, so in the space on which we construct the probability distributions, we can fairly easily construct the cost to go and the optimal input, either in an approximate way or exactly if we're able to solve the dynamic programming iteration. And what we're looking for is the cost to go in the probability space and the optimal state input distribution. So these are the complex objects that we were not able to characterize so far. And this is our main result here, namely what we call the separation principle. So the first thing that we say is that the cost to go in the probability space is not an arbitrary function. It's not an arbitrary function of probability distributions, but it's a very specific one. And namely, it is a multi-marginal optimal transport problem. So I'm trying to match cheese with wine, with bread, with the fondue, and so on. And interestingly, the transportation cost, so the cost that it takes me to move, to match some cheese to some fondue, to some bread, and to some wine, coincides with the cost to go in the ground space. So with the problem that we've just solved before, and with the problem that has nothing to do with probability distributions. So here, what I'm trying to do is to, assign every robot or match every robot with, with a reference. So with the reference at time k, with the reference at time k plus 1, and all the way to the reference at time n. So to make this separation principle even more apparent, we found an expression for the optimal state input distribution. And mathematically, the expression does something like that. In fact, what this expression is telling us is to do something very simple. So to construct the optimal input in the probability space, what you should do is to initially find the optimal input in the ground space. So forget about the fact that you're working in the probability space and find the optimal input in the much easier ground space. Then take the optimal transport problem that we've just seen, and take the optimal transport problem that we've just seen and find the optimal matching. So match the fondue with the cheese, with the bread, and find that. And then the optimal strategy is to dispatch the robots as prescribed by this optimal transport plan, and then tell the robots to use this input in the ground space to follow the allocated trajectory. So in a sense, this is telling us that the low-level control of my robots and the fleet-level control are two decoupled problems. So initially, what I can do is to focus on one robot only and forget about the fleet and get this optimal input UK. Once I know that, I need to solve an optimal transport problem that tells me which robot will have to go where. So which robot will have to follow which trajectory. And then finally, I can simply say, okay, you are robot A, you were assigned to that trajectory, just use this input UK to follow that trajectory. So the fact that this strategy is feasible, does make sense, right? You just solve an assignment problem initially, and then you just use standard, let's say, dynamic programming to go to the desired target. So feasibility is not very surprising. What was very surprising for us is that this simple strategy is actually optimal. So initially, we didn't think that the solution in the ground space was any informative for the fleet. So if you optimally want to steer a fleet, well, why should the solution of a single robot be any relevant? Why should you care about that? And yeah, this was very surprising for us at the beginning. But in fact, what this simple strategy is actually optimal. And what was this is not like some hidden convexity assumption or some something that holds in a small grid or maybe only in an LQR setting. So this result holds in what we call very general Polish spaces. So this can be grids, can be Euclidean spaces, can be infinite dimensional spaces, can be any space you want. And also you have this holds with zero assumptions essentially on all the functions that are involved. So on all the cost, on all the dynamics, you just need this very, very weak measurability, which is just the bare minimum to make sure all the expressions make sense. But this can be non-convex, non-differentiable. It could be non-linear in any way, and this result still holds. Good. Let me pause for a moment and ask you if there are any questions on that.
And Nicolas, do you need to? So this is some kind of like a it is not a certainty equivalence, right? Because you're not instantiating, but you compute the optimal input from any given state, right?
Yes, so I will illustrate it with a short example later, but it's essentially you need to understand how to steer one robot to, from every starting location to every target.
Right. So from any state, you had to compute the optimal input, and then you just apply that regardless of whether there are robots or not, or regardless of the probability mass. Right?
Exactly.
Interesting. Okay.
There's a last special case that it's I think of interest, and it's the one where the reference only appears in the terminal cost. So this was the case in the example we saw before, and this is the case in shortest path problem, for instance. There the reference is not in the stage cost but only the terminal cost usually. So in general, this function g only depends on the state and on the input, but does not depend on the reference. And of course, our result still applies. And in this case, what's particularly attractive is that the optimal transport problem that we need to solve for the assignment is just an optimal transport problem with fondue and cheese. So there's no bread, there's no wine. It's just two items that we need to match. So computationally, of course, this is more attractive. And for the input, we get the same optimal solution, and the same separation principle holds. So you would compute the input that the optimal input in the ground space, so the optimal input for each robot, and then you would solve this matching problem to decide which robot has to go where. So let me try to go back to the initial example and try to instantiate these results there. So we go back to our grid with some obstacles here and there. We have our fleet of drones and our target locations. And now we can deploy our recipe to compute the optimal strategy for this fleet. So the first thing that you would do is to start with the first robot, pick one of the target locations, and then you would compute the optimal input, which for instance would follow this black path. Then you would repeat the game for the next target, and this would give you another optimal input. And then you would repeat the game for the next robot with another target, and this will give you another optimal input. So this is the optimal input of going from one target location, from one initial location to a target location. So you repeat that for all drones, and then what you're left to do is to solve an assignment problem. So you have to decide which robot has to go to which location. And then once you've decided that, so this robot has to go to this first location here, then you simply say the robot, okay, follow the input that from the ground space, that from forgetting about the rest of the fleet, and just go there. And again, what was surprising for us is that feasibility, of course, is clear, but optimality was very surprising. And if you do that, you see that your fleet of drones will actually make it to the target. Good. So this brings me to the conclusions. There's I think three main lessons we learned from this work. The first one is that from this, we were aware that we could model stochastic system via probability measures. This was a fairly intuitive thing. We were not so aware that we could model multi-agent system via probability measures. And this poses you some more mathematical analysis. But there's very nice tools like dynamic programming, which holds in very abstract spaces, or optimal transport that we've just seen, that allow us to study this optimal control problem in the probability space. And the main result we could derive is this separation principle. So again, the low-level control of the fleet of the robots and the fleet-level control problem are decoupled. So in the sense that you first need to solve the problem for each robot, just forgetting about the fleet. And then you can solve a simple assignment problem that tells you which robot will have to go to which location. So this is not the end of the story for us, of course. We would still working on extensions. For instance, what if your robots have noisy dynamics? What if you care about functionals which are not optimal transport? Maybe you care about the variance of your fleet, or you care about some other quantity which is not an optimal transport cost. Or what if you let your horizon go to infinity? What can you say? So these are all directions for future work that we are currently investigating. And with that, I'd like to conclude. I leave you with a preprint of the paper currently on archive, and with my contact details. Please, if you have questions, there's anything you would like to discuss online, offline, or you have research ideas that we could work on, please do not hesitate to get in touch. With that, thank you very much for your attention.
Thank you very much, Nicolas, for the nice talk. I think I can open the stage for questions. You can simply unmute yourself or write it in the chat.
Okay, I'll get started if I may. So Nicolas, yeah,
Go ahead.
This is all very interesting. Which, by the way, have you ever seen the work that Nick Roy has done on planning in belief space?
I have not.
Yeah, take a look. I think the whole thing is, the whole concept is wrong, but it's sufficiently close to what you're doing that you may have to reference it. You know, just
Okay.
Or take a look. Okay, so I'm not fond of the work, so I'm not saying he has already done it. Okay, but just for your background. Now, so the okay, so I understand the point I was making before. Okay, so essentially you compute at each state what will be the optimal input, but then once you realize it, right? So you have a discrete number of robots, right, at any place, right? So how do I decide what they do?
You mean?
Oh no. Okay. Because fine. Okay. So, but then the next question is probably something that you hinted at in your conclusion, is that you're assuming that the dynamics are deterministic, right?
Yes, in this setting, yes. There's no noise, so we exactly know how the state of each robot will.
Right, but once the state update is no longer deterministic, you may lose some of this separation.
Yes. So so what we so I can tell you what doesn't work. I don't know what works here. So if you simply use standard stochastic dynamic programming, you would still get a cost to go, right? And you can still use the same strategy that you describe. Well, this doesn't work. So if you just just put an expected value in the dynamic programming in the ground space and try to work with that, this will give you something which is suboptimal. So we're still working on how can you incorporate noise. What sort of results can you generalize? We have some ideas, but we're not there yet.
Okay, and
the thing is that noise might sometimes the noise will help you, right? Maybe the noise will actually push one robot to where it should go, closer to where it should go, and then this will change what you should do in the assignment problem. So the noise, in a sense, makes everything a bit more complicated. I think we can still, but we're not there yet.
So this was for discrete, because the example was on a discrete space, right? But this holds also on continuous spaces?
Yes, this holds on discrete, continuous. It holds even it holds even if your space X is infinite dimensional. It holds even if your space X is already a probability space. It still already still holds. So it can be very general. Okay,
but essentially the point is that at this point your result is that as long as the transition function, the derivative, the dynamics are deterministic, then you can decompose this way.
Yes. And if your cost, that you have in your control problem are optimal transport costs. If you go to other costs, which, for instance, the expected value is part of that category. Optimal transport includes all the passage and distance, so it's a quite rich class of functions. But there are functions which are not there. So that's another direction in which we are going.
Sounds good. Thank you, Nicolas.
Thank you, Emilio.
Can I ask a question, Nicolas?
Yeah, sure.
It's a quick one. Just for you to know, there's also a couple of questions in the chat. But my question is about this. So what is basically a matching problem, right? So at the end, you need to do this assignment problem, which is kind of a matching problem on a bipartite graph, right?
Yes.
Like when you, and that's alone, like, it's an interesting problem, right? So there's also algorithms to do it efficiently, or algorithms that converge to stable matching, where the matching is not optimal, but agents are not willing to switch places for the assignment. That's have you just looked into how to do this assignment without going through the n square enumeration of all possible things, or is it I don't know, do you think there's something interesting to be done there?
So I think yes, we have not. So far we focused on the structural properties, so this separation. Of course, what you can do is to specifically focus on dynamic programming in what we call the ground space, on the matching problem, and try to push them as much as possible to find, let's say, better algorithmic solutions. We have some results in these directions. For instance, some stability results if you are suboptimal in solving for the cost to go in the ground space, so if you are suboptimal in solving the matching problem. But we haven't pushed that direction a lot. So yeah, so the answer is yes. I think there's something to be done there, but we haven't done that yet.
Okay, thank you. That's interesting.
I think I can read the questions in the chat.
Sure.
So the first one is if the cost distance is same, whether they are on same point or on opposite direction, cost is same. Two same distributions will be obtained. How will we choose in between the two? So
in general, maybe I can point on which I should put more emphasis, that when you solve an optimal transport problem, the two distributions that you give as an input are fixed, and you just find the optimal way of transporting the mass from one to the other. So when I ask myself how to transport the cheese from the cheese production locations to the fondue places, I don't give you the freedom to change the locations of those places. These are fixed, they're frozen, and then I'm just finding the optimal way to deliver the cheese or the probability mass. So whenever we do optimal transport, we don't need to choose between probability distributions or distinguish them. They're given, and from given them, we try to transport one into the other the most efficient way. If that answers.
I think so. The other one is, I don't quite understand the multi-marginal optimal transport case. In the example, why cannot we first consider cheese fondue transport and wine fondue transport separately, and then add the two costs together?
Yeah, that's an excellent point. It is correct. So in some cases, if your function G has some special structure, then you might be able to say, okay, I don't need to solve the matching between 4 items. I can simply match the cheese with the fondue, I can match the wine with the fondue, and I can match the bread with the fondue, and just add, combine these solutions together. So in some cases you can do that. It depends on your function G. So if some function G is general, then you cannot. If your function G is, for instance, G of xy plus G of xz plus G of xw, so there's a sum, then you can do this sort of use this sort of arguments to separate the problems. So it's up to you. If you pick a nice G, then then what the comment is correct. If you pick a general G, then no, unfortunately, we need to match the 4 items together, which is of course a bit more difficult, right? If you just can proceed in pairs, it's desirable, but unfortunately, that's not always the case.
I have a quick question, maybe. Great work, Nicolas. I was wondering, so in the robot allocation problem, if I understand, every particle, every robot is independent. And sometimes people may want to enforce collision avoidance constraints between the robots. So are there ways to enforce such constraints in the optimal transport formulation?
So hi, Thomas. Nice to see you. And so classically, the optimal transport problem does not have collision avoidance. So this, let's say, something extra that you can, however, verify a posteriori. So, for instance, optimal transport is a very rich theory. People have worked on that. I mean, Nobel Prizes, Fields medalists, and so on for decades. So, for instance, you can prove that it is never optimal for two drones to cross each other. So this drone will never go here, and this drone will go up here, because the two lines would cross. And you can prove this will never happen. So you can prove such, use such statements to say something more about collision. But this is, let's say, a posteriori things that you can say a priori. This could happen.
Okay.
Does this answer?
Yeah, sounds great. Thank you. Yeah.
Thank you.
All right. Last round. Anyone? Let's say last call. Anyone with a last-minute question? Please.
Hi, Nicolas. A nice
Hey, Karen.
presentation. So back to your example of this cheese and the fondue. So can the transportation, like a transport cost, cover like how much cheese and fondue it take? For example, if I transport a lot of cheese from one location to the other location, the average cost would be decreasing.
In the classical formulation, so the one that I've presented so far, no. So every time you pay this G, which is independent of the mass that you displace, times the mass that you display. Yeah. So that's the classical formulations. Now people have considered extensions where what you've just described is can be modeled. However, these extensions become a bit more difficult mathematically. So they haven't been so popular in practice. Now, does our result continue to hold if we go to these extensions? That's a great question for future work. I don't know. I think some of the structure will be preserved. So I'm optimistic that we can still say something, but we haven't considered this case.
Okay, thank you.
You're welcome. Thank you.
Hey, Nicolas. If we still have time, I'd also like to follow up with one question.
Sure.
Which is related to, I think if you go to slide 18, maybe it will be easiest to make the point or ask the question. Which is the grid. Yeah, exactly. Any of these works, actually. I was just wondering about the complexity of the algorithm and whether one could reduce it. So if I got it right, you said that first we would solve for every drone, the optimal path to each of the targets, and then solve the matching problem, right? An assignment problem.
Yes, exactly.
Now, knowing that you solve an optimal transport problem later / an assignment problem later, could you exploit that information in order to reduce the combinations of drone to target location pairs for which you would need to compute an optimal path? For instance, you said they never cross, two drones never cross. Does it then make sense, say, for the lowest drone to consider any targets beyond a certain level?
It's an excellent point. It would actually be, as you said, very attractive, because you would need, could rule out some of these origin destination pairs. Intuitively, I would say yes. The only tricky point is that in the optimal transport problem, so in the assignment problem, the transportation cost there is the cost to go in the ground space, right? So this is somehow, only to formulate this optimal transport problem, you need to have a certain degree of information about the ground space.
Yeah, exactly. And I was wondering if you had thought about that part, or which conditions in general would need to hold if one can find some.
Yeah, we naively thought about that, in the sense that we think something can be done in that direction, but we have not gone into the details. I think so. That you can at least rule out some combinations without any without loss of generality. But how to exactly do that, I don't know.
I was exactly. I don't have an idea either right now. I was just curious. And do you think that this would make or help your approach a lot, especially if you have a large fleet? If you need to compute these pairs between 10,000 target locations and say 10,000 drones.
Yes, for sure. I'm sure in practice, this is something someone would do. Probably in practice, you wouldn't even solve the problem in the ground space. You wouldn't solve it to optimality, because it might be very costly. So yeah, these are all very, very important questions that when it comes to deploying all these results in practice. And yeah, they are in the list of things to do.
Great, cool, thank you.
Thank you, Mark.
All right, I guess that's it for today. Thank you very much, everyone, for joining. Thank you very much, Nicolas, for giving this nice talk. And I guess see you next week.
Thank you very much for having me. Have a nice afternoon.
Bye-bye.
Thank you, Nicolas. Bye-bye.
Bye.